Welcome to this lecture series in real analysis. In this lecture, we'll show that any ordered field contains a copy of Q. I promised that we will be talking about real numbers in this lecture, but I have delegated that to the next lecture. And let us recall a few things. So we have discussed what are rational numbers, and we have discussed how to define an ordering on rationals. And then we saw that integers have a natural copy sitting inside the rationals. And then we abstracted everything out to a notion of ordered fields. Basically, fields capture the algebra that is there in rationals, and ordered fields capture the additional order properties. So in this lecture, we'll see that ordered fields contain a natural copy of rational numbers. All right. Here are some problems for practice. It is very important to solve problems because without solving problems, we will not learn anything. Let me comment a little bit about this problem. So here f is some ordered field and a and b are elements of f. And then we have defined x as a plus b by 2. Now what does that mean? A plus b is an element of f because in any field you can add two things. By 2 we mean 1 plus 1. 1 is an element of f, which is the multiplicative identity. So 2 is defined as 1 plus 1. Now what does that mean? This is nothing but a plus b times 1 by 2, where 1 by 2 is the multiplicative inverse of 2. So that is how we define division in a field. I should have said this, and in this lecture I'll highlight it. But before we start the lecture, of course, I need to explain what this problem means. All right. So first we will show that any ordered field has a copy of the integers, and not just an algebraic copy, a copy that respects the ordering. So fix some ordered field. Then for any natural number n, we will write n dot 1 to mean 1 plus 1 plus dot dot dot. How many times? N times. So this is a definition, and one can easily verify that m plus n dot 1 equals m dot 1 plus n dot 1. And again, this plus is happening in the natural numbers, and this plus is happening in the field, even though we are using the same symbol. All right. For any natural number n, we write minus n dot 1 to mean the additive inverse of n dot 1. So suppose we want to know what is minus 3 dot 1. First you find 3 dot 1 and then you just take the additive inverse. Okay. So nothing, this definition should not be confusing or convoluted or anything. This is a very simple definition. And I should also mention that 0 dot 1 is by convention taken as 0. So let me write it here. 0 dot 1 is 0. So yeah, I should have said this 1 refers to the multiplicative identity of the field. Do not confuse this with the natural numbers. Well, even if you do confuse it with natural numbers, it is not wrong, but then we will be talking about something else. So this, I should have said, is the multiplicative identity of the field, and this is therefore an element of the field. This is a natural number, but this is an element of the field that we are talking about. Similarly for this thing, and here when we write 0 dot 1, 1 refers again to the multiplicative identity of the field. 0 is the integer 0. So with these two things in hand, for any integer, let's call it, I don't know, let's say a, for any integer a, we have a definition of a dot 1. A dot 1 now makes sense. Okay. Let us note that if m dot 1 is 0 for some integer m, then m is necessarily 0. So here again we are assuming that the additive identity and the multiplicative identity are distinct. as we had mentioned in an earlier lecture. So that assumption is there. So under that assumption, I don't know if I really need that assumption, but let me make that assumption anyway. We do not care about fields where the additive and the multiplicative identity coincide. So we want to show that if m dot 1 is 0, then m is necessarily 0. Okay, and this is in an ordered field. In an arbitrary field, which we haven't talked really, we haven't seen any examples of fields, but we need the order property. So first assume that m is positive. I mean, we are proceeding by contradiction. So if m is positive, if m is a positive integer, then we know that we had shown one of the properties was that 0 is less than 1. And since you can add a positive entity on both sides and preserve the inequality, we would get 1 is less than 1 plus 1. So this is less than 1 plus 1, which again by the same reasoning is less than 1 plus 1 plus 1. And if you keep going, at some point you will reach m once, which is nothing but m dot 1. And hence m dot 1 would be greater than 0 by transitivity. So if m is positive, m dot 1 cannot be 0. By similar reasoning, if m is negative, m dot 1 cannot be 0. And hence the only way m dot 1 can be 0 is when m is 0. So that is a very simple proof. Then a corollary of it is, let me just record that as a corollary rather than a lemma. So this map, which takes the integer m to m dot 1, is injective. That's an immediate corollary of the previous one. How? Suppose phi m equals phi n for some integers m and n, then m dot 1 equals n dot 1, which would imply, and this needs to be proved, that this implies m minus n dot 1 is 0. So maybe I should have highlighted another property before we came here. So the property that I want to highlight is, this is an exercise. So m plus n dot 1 equals m dot 1 plus n dot 1 for all integers m and n, and m times n dot 1 equals m dot n dot 1 for all integers m and n. So this is an exercise. Very simple. All right, and now we have this corollary about injectivity. So if m and n had the same image under phi, then we would have this, and hence we would have that. But now use this one to deduce that m minus n must be 0 and hence m equals n, which shows injectivity. So there is a copy of z inside f, and because of the previous lemma, it respects the addition. Because of the previous lemma, phi m plus n is equal to phi m plus phi n, and it also respects the multiplication. Phi mn equals phi m phi n. Yeah. Okay. All right. So so the next one is, this is order preserving. This identification or this injective map from integers to the field is also order preserving, as can be seen by this argument here. So let me also leave this as an exercise. It's this, basically, the argument is here. Okay, so we have seen that every ordered field has a natural copy of the integer sitting inside it. Previously, we saw this argument for rational numbers, but rational numbers are also ordered fields. Okay. So this generalizes the previous observation. Now we will show something more. We will show that ordered fields actually have a natural copy of rationals. So this obviously is more than what we just did, because rationals already contain a natural copy of the integers. Again, so fix an ordered field, and we have this notation. For alpha and beta in the ordered field, we write alpha by beta to mean alpha times 1 by beta, where this is the multiplicative inverse of beta. Of course, to do this, we need to assume that this is non-zero. So you have a non-zero element beta and some element alpha of the field. We write this to mean that. And this is consistent with the rational numbers. When we have the rational number, let's say, for example, 2 by 3, this is some, equivalence class of whatever, but you can also interpret it as this rational 2 times the multiplicative inverse of 3, where of course 2 means 2 by 1 and 3 means 3 by 1. So this, the definition of this was something, it was an equivalence class of something, but the way we defined the multiplication of rationals tells us that this is actually also equal to this product. So this notation is consistent with what we already do for rationals. There is no conflict of notation. Okay, so with that, we can state this lemma. Suppose we have 4 integers where b and y are non-zero, and these two rational numbers are the same. Then these two things are also the same. So a dot 1, b dot 1, x dot 1, y dot 1 are elements of the ordered field. So these two things are also the same. This is nothing, because to prove this equality, first of all, note that b dot 1 is non-zero and y dot 1 is non-zero, as we just showed. Since b and y are non-zero, b dot 1 and y dot 1 are non-zero. So this makes sense, this whatever is written here. So to show that this is equal, this side is equal to that side, we may just show that if we take the difference is 0. So just consider this difference. But this is equal to a dot 1 times y dot 1 by b dot 1 times y dot 1. So what have we done? We have just multiplied y dot 1 above and below, right? That's all that we did. And this makes sense because this is some element of the field, call it alpha. We can multiply it by 1, and hence we can multiply it with y dot 1 divided by y dot 1, because this is 1. That's all that we are doing. So this minus x dot 1 times b dot 1 divided by y dot 1 times b dot 1. So here we are multiplying by b dot 1 above and below, and hence this is equal to a dot 1 y dot 1 minus x dot 1 b dot 1 by b dot 1 y dot 1. We are really mimicking what we do in rationals. The formal justification of this equality is distributivity. This guy is getting distributed over this difference is all. So this was a dot. I've somehow written as a minus. This was a dot. Okay, but note that, this I should have noted perhaps in the previous slide, but note that in general, m dot 1 times n dot 1 is nothing but mn dot 1. A very simple thing. Yeah. So this is equal to ay dot 1 minus xb dot 1 divided by that, and hence this is equal to which is equal to 0.1 divided by this thing. Yeah, why? Because when we say these two things are equal, we just mean that ay minus bx is 0. So this is 0.1 and hence this is 0. So this difference is 0 and hence these two things are equal. This is in some sense a tautology, in some sense, but still requires a proof. So just make sure that all of these are formally justified using the field axioms. I haven't been very, very pedantic here, but just make sure that you follow that. The field axioms justify each of these equations. All right. So we see that something like rational numbers is happening inside this. So now to finally put an end to this discussion, now what we can do is define a map capital phi from the rationals to our field as phi of a by b equals a dot 1 by b dot 1. This is our definition, and that's it. So exercise, show that phi is well defined. This is immediate from the previous lemma. This well definedness is basically this statement. So that's that, and show that phi is injective. So this injectivity is the converse of the previous lemma. If you have this, then you want to show that. You can just reverse these steps. Okay, phi is injective, and further, it's an important point to note that it preserves ordering. So show that phi preserves order, which is to say that phi alpha is less than equal to phi beta for some rationals alpha and beta if and only if alpha is less than equal to beta. So those are the three things. So therefore, this has a natural copy of rationals. Phi is a very simple, very natural map, and this shows that this contains a natural copy of the rationals, which preserves the ordering, which is one more thing, it preserves the algebra. So show that phi alpha plus beta equals phi alpha plus phi beta, and phi alpha times beta equals, and one more thing, phi of the multiplicative identity is the multiplicative identity. All of these are very, very simple, trivial exercises, in fact. So the map phi, first of all, has puts the rationals inside F injectively. So there's a copy of rationals inside F as a set. Then it preserves the algebra. And then finally, it also preserves the order. So everything that you can do do with rationals, you can do inside F using this identification. And lastly, I just want to make this diagram. We have integers. We saw that how one can put integers inside any ordered field. And then we already had seen that how you can put integers inside rationals. So this was just an integer going to this guy. And now we have this map capital phi. Just note that this diagram commutes. So either you can directly go from Z inside F, or you can go this way. So the way we have put rationals inside F is consistent with how we put integers inside rationals and integers inside F. So just wanted to note this. And therefore all of these are somehow natural. This is a natural construction. We will not go into the details or the rigor of the word, how one can formally say this is natural. We don't need to know anything about that. But it should feel natural at the very least. Alright, so there is a natural copy of rationals in any ordered field, and that was the punchline of this lecture. Lastly, a point of notation. Because of all this, if f is an ordered field, for any integer m, we write m dot 1 as m itself. So this is an abusive notation because one can get confused whether or not whether we are talking about an integer or an element of the ordered field. But in context, this does not cause any confusion. Okay, so we just replace this by that. It's simpler and better to look at, and that's all. So since anyway there is a natural copy of rationals inside f, or integers inside f, both ways, it is just better to stick to the notations that we use for rationals rather than this cumbersome dot one every time. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.